Okay, so now we've started the recording. Okay. All right. So my name is Joe Hellerstein. I'm with a part of the University of Washington called the eScience Institute. We primarily deal with issues relating to the analysis of data. If you've probably heard the term data science before, I'm sure. My formal training actually is in computer science. Have a PhD, and I've worked at several research institutes, including primarily IBM Research, and then I was at both Microsoft and Google. And so my transition to computational biology has been more recent. A lot of what I'm doing is, as a starting point, besides learning a lot, of course, is applying a lot of concepts that are very much a core part of computer science. And you'll see that in especially some of the subsequent lectures, the ones on verification and validation, which I'll give tomorrow, and then some statistical elements that will be discussed on Thursday morning, having to do with something called cross-validation, if that's a new term for you, and then also design of experiments. So I give this in part as background because I certainly am sensitive to the fact that this is a very diverse audience. I certainly saw a number of postings when people signed on to Slack where the entire professional career really has been more as a bench scientist or managing bench scientist, and really have no background in terms of the computational modeling. So I'm do not. Certainly I'm sensitive to the fact I don't want to overwhelm you. At the same time, I do recognize there are others that have more sophistication. So I'm trying to find computational sophistication. I'm trying to find sort of a balance here where hopefully both audiences will get a significant part out of this. So I've divided up this this session, so a 3-hour session on parameter fitting, into about three subsections. The second one potentially is optional. The first part is, what is parameter fitting? Why are we doing this? Now, I'll get to that in just a second, with a modest set of exercises that, you have to decide, the level of depth that's appropriate, but I do provide a separate notebook that you can run on Colab, which has the answers to them. Oh, by the way, if you've not done so already, if you haven't done this recently, you should download the notebooks again, copy them over. I have made some modifications this morning. So if it's been more than a couple of hours since you copied them over, during the course of the slides part, which will probably last about 20-25 minutes, you probably would want to copy over the Colab notebooks. So that's the first part, and that's really to ground you in some of the core concepts related to parameter fitting, which will largely build on concepts that Herbert has gone through over the last couple of days on the modeling part. Just how do you construct a model and then be able to simulate a time course. The second part is optional. We'll see how much time we have for that. I want to sort of judge that to make sure we get to the third part. But the second part deals with addresses some of the technical details related to parameter fitting. It fundamentally requires some mathematical and computational techniques that are generally referred to as optimization, where you're systematically searching for a best solution, where best has to do, in this case, technically, if you're familiar with the term residuals, you're trying to minimize the residuals, the difference between what your model predicts and what you have available to you from observational data. And then the third part is actually doing the parameter fitting. And the sort of punchline from the story on the first part is that there's no way to ensure in general that you really have the right estimates for parameters. And so you have to, in the end of the day, do some sort of exploration to get a feeling for what makes sense with the parameters you found. And that exploration involves a certain workflow. It's a combination of sort of computation and scientific judgment. And that's what the third part is about. So with this background, let me go ahead and then talk about parameter fitting. Again, I would say this first part is suitable for all audiences. I think that Even if you have a computational background, you may not, unless you also have a statistical background, the parameter fitting idea may be something that's new to you. So what is parameter fitting? Why is this something that's important? So I think you've already been introduced to this model. This is the model of glycolytic oscillation that Jenna Wolf and company developed. It was published in 2000. There is a biomodels version of this available that you can actually download and run in Tellurium. And the core part of this and sort of the launching point for the discussion here, and this is probably, you've noticed this in the development of the models that Herbert has done as well, is this observation that there are a set of parameters, kinetic parameters, that relate to the concentrations of chemical species. And this affects the rate at which reactions occur. And the last question, for example, was really about this. How do you come up with these things? And what you're trying to do is make sure that you choose kinetic parameters that make sense in the context of the experimental data. Now, the question that was asked was actually a deeper question than this. It wasn't just about what are the values of these parameters. The question was, I don't even know the functional form that the kinetic should take. And that is a more challenging question. I think Herbert answered that. Start simple. And there are a variety of avenues that sort of qualitatively, for example, you may expect that one species may have an activating effect on the kinetics. And so you expect it to have, if you look at the kinetics formula, you expect to see, that the reaction rate should increase with that species. Others may have an inhibiting effect, it should decrease. You get those qualitative things, but there's a lot of different actual algebraic functions that could yield the same qualitative characteristics. So I'm going to assume in this talk that we actually have the functional form and we can write down the kinetics expressions. The challenging part that we're addressing here is what are the values of those parameters? Now, some of these parameters may actually, for something that as well studied as glycolysis, a lot of the parameters, are probably available, but as, anybody knows who's, dug into, anything in the real world of biology, these parameters can vary a lot, even with the same organism in different organs. And just the characteristics could be very different. So just because you know the value in one doesn't mean you know the value other. And this is assuming they've been studied in vivo as opposed to in vitro, where it's been really under non-physiological conditions. So knowing the actual values of the parameters can be a challenge. And so a lot of what we're going to do is say, we're going to try and come up with credible values of the parameters in terms of constraints that might be present physiologically, but also in terms of what's needed in order to match experimental data that's typically about some product of this reaction network, something we can observe. If we could observe the glucose level or the level of ATP, let's make sure that whatever parameters we've chosen for the enzyme kinetics through glycolysis makes sense in terms of those concentration levels, and that's what we validate against. Okay, so that's sort of the setup for this. This is a little more detailed to sort of drive home some of the challenges involved. This is the reaction network for the Wolf model. It's not a huge network. This is actually sort of modest, in terms of what you would find in biomodels, for example. You find many models that have, tens of reaction. Here we have just about 10. There are a few models that have hundreds. So they certainly can be much more complicated. These are the initial values for the parameters. The parameters actually are shown up here. Yeah, it's in this sort of purplish color. You can see where the parameters are sort of spread throughout. They appear in many ways. Some of these, like this one over here, for example, reaction J6. This is pretty much a straightforward mass action type of thing. And a lot of times what you'll see is mostly max action. So here we have, this is a bi-bi reaction. So we have acetaldehyde with NADH. And what we're doing is we've taken off the hydrogen over here and produced ethanol. And so what we've got is we've got a constant, basically, that's this J7, it's an underscore there, it's a little bit obscured K. This constant is multiplied times the product of the concentrations of the reactants. So we have those that are pretty straightforward. Then we have others that are a lot more complex. This reaction over here, for example, this begins to look more like a Haldane expression. You know, you seem to have some sort of a catalysis going on here. There obviously is an effect down below that looks like a saturating effect. So it's a variety of different ways. Oh, and then this one over here is also important. You know, it's a kind of Hill expression where you see an exponent over there. So this is probably an integer that you would expect to see there, although it doesn't have to be an integer. But it's going to be an exponent for that expression. So here are the various settings of the parameters that were used in this published paper. And as a result of the settings, then we ended up with this oscillation over here. But then the question comes up, you know, and there's a whole discussion, it's a core part of the scientific work is, you know, what are reasonable expressions for these parameters? Anyway, I'm going to use this as a running example to indicate how we go about doing and the importance of doing this kind of, and the challenges of doing the parameter estimation. So parameter estimation, just to restate that, is all about, suppose I had this data as a starting point, or, you know, some sort of stochastic version of these data, you know, because if I actually measured it, obviously it wouldn't look quite this neat. And I had maybe some initial ranges for the parameters that might be present over here, or at least constraints, you know, certain, you know, like none of the kinetic constants should be negative, you know, none of these parameters should be negative. So that's one constraint. So how would I then go about figuring out reasonable values that got me something close to these data over here? And that would really be a statement of the parameter estimation problem. Yeah, so I will actually use, just in terms of language, I'll use parameter estimation interchangeably with parameter fitting. Sometimes we also say parameter optimization. I'll use those terms interchangeably. There are some nuances in terms of the differences between what those three things mean, but for our purposes, that you can use them interchangeably. All right, so here's some of the basics if you're going to do parameter fitting. So what you're trying to do is pretty much the objective I just gave you. Find values of parameters that make it so that the model matches the experiment, the observed data fairly well. And so there's an assumption that you have some observed data. It may be as, let's go back over here. Now here we have, I don't know, like a 10, I think, or so species, chemical species. You may not necessarily have measurements of all 10. You may only have a subset. That's a possibility. So you're matching on more limited data. Obviously, if you have more data available, then presumably you can do a better job with matching the parameters. In extreme cases, and this is not something that I will discuss in any detail, it may be that without certain data, you really don't know the effect of a particular parameter. Maybe that parameter only affects one chemical species, and its effect, that chemical species effect on the others, is rather modest. So that's that can be a problem. You would you know, at that point, then you would just not be able to discover, you know, a reasonable value for that parameter, and that's what's called an identification problem. Okay, so this is our objective and sort of the limits and the context in which it occurs. The key way we're going to do this, and this is sort of comes from statistics ultimately, is this notion of what's called the residuals. And the residuals are actually really simple to calculate. It's the difference between what you observed, your experimental data, and what the model predicts. So typically we're observing floating species. I mean, you could observe reaction, you could observe fluxes too, reaction rates, but you know, in the discussion here, we're just going to be talking about floating species. So we're going to be talking about the difference between some subset of the floating species and their corresponding simulated values. That's the residuals. And obviously you'd like residuals to be fairly small. And the question is, what does small mean? You know, and a small sort of balance, because we've got residuals. If we've got, you know, 10 chemical species and it's a time course, then we've got the residuals for each one of these time courses, and then also for each species. So if we're talking about, let's say there were, 10 points at each, second of measurement here. So 50 points across here times 10, that's 500 points. That's how many residuals we have. So, we probably want things to balance. Maybe we did really well with glucose, but really bad with fructose 1,6 bisphosphate. So that's also part of the challenge with doing this work is, figuring out, have I got this balanced right? And another challenge, of course, is there can be differences in scale. One chemical species may be quite large, and its residuals, although modest proportionally, might be actually quite, might be large enough so that they may mask a huge deviation between the predicted and observed values of some other chemical species. And that's another part of the analysis, is to make sure things are scaled right, so that, if you want to get both and therefore get good estimates of all the constants, you have to have that balance in there. All right, so this is a core concept here, the residuals, and actually in the second part of this lecture, when we go through one of the notebooks, one of the key things you'll be doing is calculating residuals, so you get more of a feeling for this. All right, so here's sort of a generic algorithm for parameter fitting. The inputs to this are, you have a model, and you've been working with tellurium models already. You have the parameters you're going to estimate. In this case, we have that 16 or 17 parameters from the Wolf model that we could estimate. And we have observed values. And presumably this comes from laboratory measurement. Typically what we do for our courses is that we'll create synthetic observed values. This is not what you would do in practice, but it's great teaching aid. And what we'll do is we'll take the true values that or the true in the sense that it was generated by the model. We know what they are, and then we'll add some noise to them, like a normally distributed modest random variable, modest size variable. But in practice, you'll actually have real observational data. So these are the inputs, the key inputs. There are other things that you might specify, like you might specify constraints on what the parameter values can be. Like, it has to be within a certain range. It should certainly be greater than 0, or at least greater. It shouldn't be negative. I guess some of them actually could be 0 if they're not important. Okay, so those are your inputs. And what you're going to come up with are estimates for the parameter values. So you start out with something about which ones to estimate, or a range for which they're estimated, and we're going to actually come up with values of the parameters themselves. Okay, and here's generically the steps that you go through. So and if you haven't seen this type of thing before, this is what's called pseudo code. It's used widely in certainly in the software industry when you're just trying to describe how an algorithm would work. You're basically writing it in English mixed in with a little bit of, sort of computer language notation, like you might have down here, like here, I have a subtraction. So, that's something you could actually execute if you had a values assigned to observe, if you had actually something assigned to observe values and simulation results. But for the most part, you're just writing down in English what it is that you're trying to do. So it says here, do until you get a good estimate of the parameters, or you assume or some runtime limit. So there's a whole question here about what good means. What is good? And so what you're doing is now is you're going to assign values to the parameters. So when we talk about a setting, what we mean is all those, like in the Jenna Wolf example, those 16 or 17 different parameters, we're assigning some value to them. And somehow we're coming up with a new value for these assignments. We don't say how that happens, and that we'll get into a little bit later. But somehow we come up with a new assignment. This is our settings. Then we run a simulation using these settings. And now we have the simulation results. We already had as an input the observed values, that's up here. So now we can compute residuals. And this is what I was talking about before. Residuals really guide us along the way as to how good we are. And one way of judging good is to look at the sum of squares of the residuals and say, is this, so you want the residuals to be small. Of course, small could be, residuals could be negative as well as positive. They don't have to be positive. So by squaring them, you're assuming that they're all positive values. So now the minimum value of the sum of squares is going to be 0. So if we say if the sum of squares then is smaller than what you had previously, then save these settings. And if these residuals, if the sum of squares is really small, then you're done. That's our definition of an until good. So, Okay, let me pause for half a second here. And because this is sort of like the core idea of what goes on. I mean, definitely for those of you who are less computationally inclined, you're primarily wet lab people, and you're probably interested in, hey, I have some computational folks that are going off and doing stuff that come up with parameter values. I mean, this is what they need to do. And I want to see if there are any sort of philosophical or conceptual questions at this point.
Joe, there's a question in the Slack that basically is saying if you don't really have experimental measurements, but maybe you have a broad idea of what the output should look like, what kind of like
what might you do? Yeah, how would you go about it? Right. So there are a few different things that you might consider there. One approach is you essentially construct some synthetic functions for the output. So you have some broad ideas, you might explore that a little bit. Another thing that you might consider is picking what you think are reasonable ranges of parameter values or settings for parameter values from the literature, something that looks close to you from either other models or other experiments, and see which ones or combinations of those satisfy your constraints. Because essentially what you're saying is you have a set of constraints, not really actual time course values, and see if then which settings of parameter values then satisfy your constraints. Other questions? Okay, let me carry on then. All right, so let's see. Okay, so now I'm going to get on to sort of some caveats about this whole process. I mean, so far it sounds pretty, neat conceptually about what's going on here, but here are the things that are sort of fundamental challenges with doing this. Okay, so the first one is, at least at this point in time, and this may change in the not too distant future because of the tremendous advance with laboratory automation and data that can be produced, including time course data. But for right now, typically biological data sets tend to be small. And the number of parameters that we're trying to fit is not small. I mean, the Jenna Wolf model, there were, 10 reactions and 16 parameters? I mean, fitting, MapK, the signaling, many of the models there will have, 30, 40 parameters in them. So there are a lot of parameters to fit. And, the sort of reference point here is this quote from John van Neumann that, with 4 parameters, I can fit an elephant. With 5, I can make his trunk wiggle. You get enough parameters, you can do anything. And so we definitely have, a sense of caution here about what it means when we fit so many parameters to a small amount of data. And in the end, for the science to be meaningful, you have to have good arguments for why you chose the particular parameter values, that, it's consistent with some set of measurements or something, not just that, I ran this parameter fitting algorithm and I can fit the limited observational data I have. Okay, so that's sort of concern number one. Yeah. Okay, here's a second concern. So let's say, we're in a space where we have enough observational data. And I think that within the next few years, this probably will be pretty close to true, at least for modest sized models. We'll have enough data where we're not so concerned about the number of parameters we have to fit. We have just enough data so that it makes sense. But let's see how much computation is required. And this, I think, may be a little bit of an eye-opener for those of you who have less computational experience. I think I know many times folks with less computational experience will think, well, wow, I'll just give the problem to the computer and computers are fast and it will solve it. And that's the answer to that is yes, up to a point. And it turns out that this is one of those cases where it comes up to a point. So let's just sort of follow through this example and maybe it will drive the point home. Okay, so let's say that the system that you're modeling and in the computational environment you're working in, you can, with one single set of value, you set values for the parameters and you run the simulation. Suppose that each simulation run takes a microsecond. Okay, and so now I want to explore for however many parameters I have and however many values I'm going to assign to those parameters, and what's called an exhaustive search. So I'm going to have many different values to assign to each of many parameters. So what I'm going to show here is actually the log base 10 of the number of hours it takes. So what that means is that, if it takes 1 hour, then you'll see a value of 0. If it takes a second, it's obviously going to be negative because it's smaller than an hour. And then, this way I have sort of like a more reasonable scale, because it turns out we actually have to talk about times that are of the order of the age of the universe. So right away, this is sort of like, you sort of hear what the punchline is going to be. All right, so here's our space that we're going to explore. So here's the number of parameters. Remember in General Wolf model, we had 16 parameters. So we're over here. Boy, if you only have 2 parameters, you're golden. That's great. But most of the time, you're somewhere over here, 30 to 60 or so. And then the number of parameter settings. So this is where you're only considering a certain number of values of the parameters. Like, here we have 2 different values. We're considering 4 different values, maybe evenly spaced, and so on. So what you see very clearly is that if you have a few number of parameters, what it's sometimes referred to as factors, and just a couple of settings, sometimes referred to as levels, you're talking about, sub-second response time to do this. But once you start transitioning over into regions where you have a significant number of parameters, and really this is well within the range of most of our models, right away, you start seeing a lot of red, things that certainly are in excess of the age of the universe, like, log to the base 10, 10 to the 19th hours, basically over here. So it gets to be very expensive. Now, immediate response is, well, hey, you're talking about a single machine. I can run these in parallel. Okay, let's consider parallelism. I worked at Google. We could run 1 million cores. That was, we actually did some experiments, some stuff with G protein coupled receptors, running 1 million cores. Okay, so if you want to run 1 million cores, subtract 6 from each one of these. Okay, well, I'm still mostly larger than the age of the universe. Okay, let's say 1 billion cores, okay, so now you subtract 9. I'm still larger than the age of the universe by a large fraction for, things that are, fairly common in computation. So the observation is that that sort of brute force approach to finding the fitting the parameters is just not going to work. That in computing, we refer to these as heuristics, approaches that sort of makes sense, but you can't prove that you're getting the right thing. And so that's where a lot of times the quote proof part has to be that there's some validation from the point of view of looking at the science that makes sense for the parameter values. All right, so let's talk about a few things in terms of how you might think about what's going on with parameter fitting. And this will ultimately lead to some insights as to circumstances and sort of approaches to getting more accurate, more better fits, and also with reasonable computational expense, as opposed to running until the age of the universe. All right, so what we're going to look at here is what's called the fitting surface. So it may sound a little bit abstract, but let me explain what that means. That is that if I take 2 parameters, let's say, I'll primarily work with 2 because the visualizations get hard if you get more than 2. So let's just think about 2 parameters. If I vary these 2 parameters, suppose I know what the right answer is, and I vary these 2 parameters, at each value of those 2 parameters, I'm going to have a value for the residual sum of squares. That's our quality measure. So we have a good fit. And of course, ideally, I'd like the residual sum of squares to be 0. So at each set point, I'll have a different value for that. And what I'm looking for is the smallest value. And so let's consider a simple model here. This is a simplest model, probably, I'm sure, I believe Herbert probably introduced this on the first day as the first example. So we have a couple of irreversible reactions here, a single chemical species, It's produced at a rate K1, depending on this fixed concentration over here, and decays or degrades at a rate K2. So that's our reaction network. Okay, and so what I've got over here is K1 and K2 are the parameters we're trying to fit. And initially what I've done is I've said, I'm gonna run a simulation model. This is done with simulation. I'm gonna set K1 to 1 and K2 to 1 also. So if you look over here at the plot, you see K1 is here and K2 is over here, and you see a red dot right there. So that's the true value of these parameters. The fitting surface is what happens as I move away from the true value. So as I move away, so if you look at the scale over here, this sort of lighter color here, lighter color means that it is a smaller value, and darker color means it's a larger value. These are the values of basically the residual sum of squares. I normalized it so it'd be in similar units, but that's what's going on here. Is it's the residual sum of squares. So as I move away, it gets darker. You can see, especially along this line over here with the negative slope, it gets darker. What's interesting is that if you look along the line here of unit slope, it actually is lighter, all across there. And if we go over here and sort of zoom in, now what I've done is I've changed the scale. You see the residual sum of squares are much smaller. This line of whiteness becomes more apparent. And now the darker color here has a different interpretation. It's a smaller value than it was in the left-hand plot. So what's going on here is that as we get closer to the true value of these parameters, as we adjust it, remember in our algorithm, we're iteratively selecting new values. What's happening is the residual sum of square keeps on decreasing until we get to the actual true value. This is not a common phenomena. It does exist. It can occur in some networks. And what it's called is, this is an example of what's called a convex function. A function, it sort of looks like if you're doing this in one dimension, the relationship between X and Y, if Y is the output, would be, it looked like a bowl or an upward shaping parabola. And the neat thing about a convex function is that what is locally minimal is also globally minimal. That means if I'm sort of greedy and I keep on moving the parameters in the direction where the residual sum of squares gets smaller and smaller, I ultimately will get to the global minimum. It's a great way of reducing computational complexity, and it's rarely going to work. I hate to tell you that part, but it works sometimes, and it's a useful thing to know when you're there. So let's go on to another example over here. That's a convex system, and this what's called gradient descent, if you've run into that term before. So let's work at something which is closer to a real world model. Let's look at the Wolf model. So now we're talking about 16 parameters. Obviously, I'm not going to show you something in 17 space where 16 parameters plus the surface be 17 dimensions. So I'm just going to pick two of the parameters. So this one I've picked J2 underscore K, J1 underscore Ki. You could look back at the reactions. This is a similar kind of plot. Again, we're looking at the normalized root mean squared error. Again, the true value from the model is right here in red. And what's interesting about this are all of these ridges. I see all these ridges in through here. The ridges indicate it's dark along here and gets light in the middle, dark here and light along here. So if you do what's called gradient descent, if you're sort of greedy and you keep on looking for smaller and smaller residuals, you'll get stuck in one of these valleys. So if I started out here, if I had the bad luck to say, okay, here's my starting point for my search, and I'm going to use gradient descent, I probably would be stuck somewhere over here, and the true value is over there, and I wouldn't find my way out. So you need to have an algorithm if you're dealing with a non-convex function. And again, almost all of what we're going to be doing is non-convex. You need to have something that jumps around. Now, that said, what's sort of curious here is some of these algorithms that jump around will not necessarily get you to the bottom of the valley where they are. So it might find something like up here, but not get you down to the bottom. And so sometimes it's good to do one of these non-convex kinds or non-gradient descent kinds of algorithms, and then do gradient descent to make sure you're at the, locally at the lowest value. Now, probably you're not finding the true value, but you're closer. All right, so gradient descent can get stuck in ridges. So here's sort of a summary. And again, I'll do a little pause after this before I go into the computational discussions. So when we talk about, fitting and the complexity of fitting, what are we concerned about? We're concerned about the surface. So if we have a convex surface, easy guys, just gradient descent, we can find it. Problem is we just generally don't know if it's a convex surface or not. So the easiest thing to do is try it with a gradient descent algorithm, see what you get, see if it makes sense, see how good the fits are. That's really the best way to do it. Okay, so number of parameters, number of level settings, we talked about that. Boy, the more parameters you have to explore, the more level settings, the more computationally intensive it gets. And then the other thing that you get is this where you start. That makes a difference. Boy, if you have the good fortune to know where you're going to start, if you get close to one of this trough over here, and I say start on that ridge, you're golden. But yeah, how did you know how to do that? And so it's an argument for trying many different starting points, basically. Okay, and then I mentioned that search algorithm, we'll see how much we have a time to do that, but at least in general terms, you understand that there's this notion of gradient descent, which is great for convex curves, but not really so good for something like this. And there are other algorithms. The one that we generally use is something called differential evolution. I won't go into a lot of details about it. We don't have time to do that, but just keep in mind that that's good for these non-convex surfaces. Okay, and I think, yeah. Okay, so here's the punchline from this first part, and that is that fundamentally, since we don't know this surface here, I'm showing you this because I've done some controlled studies, but generally we don't know this surface. This is an exploratory analysis. We want to see if we can, sort of like, do we feel lucky? And we try maybe a few starting points and do gradient descent, and then we may want to do something else as well. And then the third part, which I may get to sooner than expected with an abbreviated second part, is that you want to have an environment, in this case, I'm proposing a tool, that allows you to explore different factors in doing this, where you start, the search algorithms, maybe which columns you're using in your analysis of residuals, all that. You want to be able to do that and sort of have a workflow that allows you to iteratively explore. Okay, so at this point, let me see if there's some questions. I haven't looked at chat. Did anything?
Yeah, I was going to say there was a question in the chat. What was it? Is parameter fitting somehow related to inverse problems?
Okay, I'm not sure what, because there are a lot of different kinds of inverse problems. I guess it's inverse in the sense that you're, instead of going from a model with parameters to a prediction, you're going from predictions back to the parameter value. So I guess in that sense it is. I'm not too sure if there was more to it, like maybe there were particular computational techniques which were being proposed that were applicable for a particular kind of inverse problem. I'm not sure if the questioner wants to say more. Okay.
So
all right. Anything else that you saw? Go ahead, Lucian.
No, it was the person was Julio. So if they want to say anything else, go for it.
Yeah, go for it. Right.
Someone else is asking, it seems related to machine learning. Is SB-STOT a tool that includes machine learning tools?
Okay. Yeah, there is a lot of overlap between what people call machine learning and statistics generally. The concepts, a lot of them are drawn from statistical techniques developed, 20 or so years ago, and then have been, with the advent of very high-speed computing, have been sort of generalized in many ways. So some courses on machine learning will include even basic statistical techniques like logistic regression and even linear regression as examples of machine learning. So, with that sort of very broad view of machine learning, I guess the answer has to be yes. So I don't know if there was something deeper here. I mean, I think there is another level to this where you might ask the question, gee, you're going through all, later on when you see the sort of interactive exploration that goes on when you're doing parameter fitting, you might ask the question, could some of this be automated? And could there be a neural network or something else that guides you much more effectively? That's probably true. I think our understanding about how to do the interactions is still, we're still developing sort of best practices. So maybe a little bit harder to codify it. So was there, again, let me leave this open if the questioner had a follow-up.
Sure. And then one person, there was somewhat answered in the chat also, but just was talking about like, what is a global minimum and a local minimum? Like what do you mean when you say that, I guess?
Okay, excellent. So let me, because if not everybody may have read the chat. Okay, so if you see the red dot here, and this is a little bit hard to see because it's small, you can see that this down here, that it's the widest part of the widest part over there. And that's what we found is that's the global minimum, because it's the part which is actually 0, because that's actually the true value for these parameters. But
and more specifically, and then that means that those are the values for those. If you use your J1KI and J2K of 1 and 10 respectively, you fit the data to the lowest, like
the lowest value for that, right? Those are actually the true, since we know what values were because we generated the data,
right?
That then that is actually you will actually get a residual of 0,
right? So
yeah, that would be the
generated data is
minimum.
compared to the experimental data is as the
in this case
lowest least squares, which is exactly the same. Yeah. So in this case, but
right. So what local minimum? That's a global minimum because you have the lowest value of the R squared. But suppose you're over here. You see how that's darker? These R squareds are clearly larger than over here, but it's in a valley. So locally, I can't move any direction and get a smaller value of R squared. So locally, that's a minimum, but it's not the global minimum. It's not the best. And that's the whole thing about a non-convex surface, is in a non-convex surface, you can locally be at a minimum. I've done gradient descent to get down to the minimum value. I'm at the bottom of this valley, but I'm not in the lowest part. I'm not at, all the way off the mountain. Whereas over here with a convex surface, once I go down to the lowest part, I'm at the minimum, and I don't have to worry about these other ridges and things.
Yeah. One way to describe it might be like, if you drop a ball outside, it will roll downhill and then stop, and it won't be at sea level probably because it will get in a local minimum. It'll roll down until it has to roll up somewhere, right? But it won't have made it to the sea yet. Right.
That's a great analogy. Okay. Anything else that you saw in the chat that I should address?
I think that's mostly it.
Okay, great.
Yeah.
All right.
I guess the only other thing I would say to just as an interesting other thing to think about is that your data itself will have errors in it. So there might be a difference between the best parameters for your specific data versus the best parameters for the truth, because your data doesn't fit the truth exactly.
And that's a good point. And that actually gets onto this idea of the uncertainty of a fit, which is a great point. And this is something that I will touch on. There are many different approaches to this, but I'll talk about one particular technique on Thursday morning for addressing this exact question that Lucien raised, this issue, with a technique called cross-validation, how you might be able to assess that, both for the model and for the parameters.
Yeah.
All right, so I'm going to switch over to.
Sorry, could you think of that as like overfitting? So like a problem of overfitting your parameter or your parameter estimation, or.
I'm sorry, I didn't really understand the question yet. I may have cut you off.
Oh, I was just talking about the discussion that Lucien and you were having, and the fact that just because the parameters fit your data, they might not fit the actual question that or they might not represent whatever you're studying. So would that be a problem of like overfitting?
Oh, okay. So I think there are two parts to that. One of them, I think Lucian was talking about a particular issue for the reason why the fits you came up with may not be the true values of the parameters, assuming that you think of this in terms of true values, and that is because your data itself is imperfect. So I think that's what he was talking about. And then. Sorry, there was one other thing you
Overfitting
said.
was the other thing.
Oh, overfitting. Thank you,
Yeah.
Lucian. So then the other part, now the overfitting, to some degree, that's what I was bringing in that quote from John von Neumann, is that, if you add more and more parameters, then you can, explain more and more, but it doesn't mean you're really adding more information. There's this notion of in statistics, what's called degrees of freedom. How much data do you have in excess of the number of parameters you're going to fit? It's a direct analogy to if you're solving a linear system of equations, how many equations do you have? How many variables do you have? If you have n equations and n variables, you can find, one answer. But if you have, n equations and, half an n variables, well, you may be over specified. You may have so many constraints you can't do it. And if you have a lot more variables and equations, then there may be many answers. And that's a lot of times our case, is it may have, if we put in too many parameters, the parameters are the variables in this case, and the equations are data, essentially, then we don't, there are a lot of answers. And, how do we figure out which one's right? And that's the overfitting problem.
One of the classic examples of overfitting I remember hearing is planetary motion. Like back when people thought the Earth was the center of the solar system, they would come up with equations that would explain the movement of the planets. And then it didn't quite fit, so they added more and more extra parameters to sort of fit things. And if you keep on adding more and more parameters, you can fit the motion of everything in the solar system, fixing the Earth in the center. But there's obviously a better system that doesn't overfit the data with the sun at the center. And then things make a lot more sense, and you don't have 50 million parameters trying to fit everything.
There's a common reference to something called Occam's razor, that the simpler model is likely the preferred model. And it goes in hand with this too. Fewer parameters are better.
Can I add something related to the imperfection in the data? Like on the other hand, okay, the data can sometimes be imperfect, but on the other hand, there can be, you can face data with a huge variability. Like it doesn't mean that they are not perfect. It just means that the several realization, for instance, of an experiment can include some characteristic for the specific experiment. So in this case, what do you do? Because on one hand, you want to fit, but you have a huge variability in the data set. So you might lose these characteristics for each of the experiment, but on the other hand, you want to fit some parameters in order to mimic the dynamics or the evolution of the system.
So if I understand the question correctly, are you saying that there's an effect where essentially the signal or the impact of this effect is basically smaller than the natural variability in the data, based on the measurements? Is that what questions you're asking?
I mean that here the imperfection of the data might come from some specific characteristic of the realization of the experiment that you might need to consider. But on the other hand, you need to make a deal with which data are you going to fit your model. Then.
Okay, well, I mean, generally there's, of course, a challenge with what you're trying to measure, or what effect you're trying to detect in comparison to the variability of your measurement system. And so if the measurement system introduces too much variability, you're going to have challenges. And there are techniques for doing this. I mean, if you do more measurements, then the average value, its variability will get smaller and smaller as you look at the data average over it. So that's one technique. I mean, this is something that there is another element of this, which is that the parameters that you're trying to estimate, they do obviously have a variability that you can assess to some degree from the data. And again, this cross-validation technique, which we'll discuss on Thursday, tries to address that. Other questions? Okay, let's get on to some computational stuff. This will be a relatively, I was going to show you a sort of an overview of the slides. I assume my screen, as long as I stay within the browser, if this is all visible.
Yep, you can still see it. Your list of the files in there, yeah.
Yeah, great, excellent. Okay, so what I was going to point to is this. So we just went through this PowerPoint slides right here. What we've got ahead of us are going to be some computational discussions. So this one here, which we're going to get to first, it will give you a chance to just get more of a feeling for this idea of the residuals. Because that's a core part of doing this. I think if you have some intuition around that, everything else becomes much easier. And it doesn't take long, just a few minutes to go through the material there. And then there's an exercise, and that's the key thing in terms of getting a feel for this. The solutions to this exercise, and there's other exercises for the other parts too, are in this this notebook right here. I separated them out so that you don't inadvertently peek when you don't want to peek. This is not a 4-grade course, so of course peek whenever you want to peek. And if you need hints, you can look there too, and it's organized by the particular exercise. And then there are 2 more slide sets having to do with some more detailed technical understanding of parameter fitting, the optimization technique, and then this sort of workflow where you're iteratively and interactively trying to do the fits. So what I'm going to do now is let me go on to this one here, which I think is this slide deck over here. So you're probably used to this now. If you haven't run your virtual machine in Colab recently, you need to at least do the reinstalls up here. While this is happening, let me describe what's going on, how I've organized this notebook. So I highly recommend that you click on these 3 parallel lines over here. It gives you a table of contents. It allows you to navigate through the notebook a little bit better. You can go across these different ones. In all my notebooks, I have something called preliminaries. These are technical preliminaries having to do with setting up the computational environment. And I'll go through it briefly this once. I won't in subsequent notebooks. In subsequent notebooks, I'll just do you can hide this thing by just pressing this button over here. So I'll typically hide it. But what's going on here is it does the installs that you need to install. We will, after the class, we will make available scripts so that you could run this separately on your machine. If you want to run it in Colab, that's fine. But we'll also make it so that you could run it separately, like within an environment, like I think you talked about Spider and maybe PyCharm, but in some Python environment. And that's what the purpose for this variable over here is Colab. Are you in the Colab environment? Imports, I assume you've already gone through imports. These are packages that are available to you from the Python repository called, sort of not the best name. It's called PyPy, P-Y-P-I, Python package installs. This cell right here, unless you're really, really interested, I would just sort of ignore it. What it does is it allows us to get information that we've stored in a common repository, something called GitHub. Lucian will actually give a bit of a talk on GitHub later on. A lot of the theme that we have in the Saro lab has to do with reproducibility, and being able to share things in a common way is very important, and GitHub has been a common mechanism for this. And the details here are less important, just that you have available to you. What is relevant is if you go down here, you will see, it's more towards the bottom here, you will see a whole bunch of stuff that you end up getting set up for free in this notebook. In particular, the examples you'll work with will be for the wolf model. that we discussed and has been discussed before. You'll get the actual antimony model right here, Wolf_model, and you'll get it as a NumPy array. And I assume you've had at least a little discussion of NumPy arrays, or you will shortly, but that becomes relevant in terms of doing parameter fitting because you need some empirical data. And this is not true empirical data. This was generated, but it gives you an opportunity to do that experiment. And then there's a linear pathway model, which I'll describe below, which is just a sequence of species, one reaction after the other, and it's similar kind of structure where you have an array. There's a slightly different organization of that data, something called a data frame. Imagine that most of you have not encountered that before. We'll discuss that later. For right now, don't worry about it. It's not relevant to this particular notebook. So that's what you're getting out of this section over here called Preliminaries. And like I said before, just ignore it. You'll have the environment if you did the run all up there. So just for everybody remembers, gets over here, run all, you press that, it should all be there. Okay, so what I'm going to do is talk a little bit about the linear pathway model and talk about what residuals mean, and then it'll get you to the exercise for the linear pathway model. And I'll talk about the exercise in just a second. So here's the model itself. This is the one I use repeatedly. There are 5 species. And then that means there are 4 reactions. This is, I guess these are all floating species, so nothing is fixed. So you'll see sort of a transient effect here where S1 has initially all the mass, and then because of the reaction as time goes on and the values of these constants, eventually then a mass tapers off to 0. Here is the, as I mentioned before, there is this sort of generated empirical data so that you can do parameter fitting. The names of the species are S1 through S5. Those are the, and then we have the array data over here. Let me show you at least what that looks like. So this is again the data that is our substitute for having actual experimental data, linear pathway. I'm going to start out by showing you the data frame form of this, just because it gives you a tabular representation. So what you have here, and you'll have this also with the linear array, it's just that you don't get these nice columns over here. It's the same data content. You have time. Time goes up in basically 1/100 of a second increments or so. It's sort of evenly spaced. Then you have a column for each chemical species. There are 5 of them. In this data is perturbed from something that was synthesized with the true values were 1, 2, 3, 4 for the 4 kinetic constants. And then we added on some random error on top of that. So we should have started out, you can see in the model here, it should have started out at 10, but it starts out at 8.5 because of the randomness. And then you should end up with all the mass is then in S5. Well, we ended up with more mass than we started out with, so that's obviously not quite right, but it's just for the purposes of this exploration experimentally, or with to show you how to do parameter fitting. Okay, so that's the data. It's useful to plot this too. I assume you've already done a little bit of plotting. What I tried to do here was just show you what the data actually looks like. It's a little bit, even though this is a neat table, it's hard to see really what's going on there. So here we have the 5 chemical species. Here's the time course. And this is, again, this observational data. I highly recommend that when you're doing parameter fitting, take a look at your data. Because one of the things that you notice right away in the way these data were generated, and in your case, the way it would be obtained experimentally, clearly there's a lot more variation in S5. And as we've discussed, many of the questions that happened after the slide set were about how can you deal with variability in your measurements? And so obviously there's going to be some challenges here with fitting anything that depends on S5. So that's a little challenge there.
Joe,
all right, so
when you generated
review.
this data, did you generate it like the randomness by a percentage, basically? Of the,
yeah, I believe it was actually it had to be by a percentage, otherwise it would end up with negative values.
Yeah. Okay.
Right, exactly. That's what I did. And obviously for the large, and as a result, for a larger value gets larger variability. So that's one of the sad consequences here. It's probably, you know, there's some basis for that, but it's also a challenge. Okay, so the core concepts that we have in fitting are where a parameter, that's what we're trying to estimate. We have observed data. Here's, you know, our case of observed data. We have fitted data, which is when we take values of parameters, we run a simulation, we come up with, you know, estimates for, you know, what we think S1 through S5 are. And then residuals, and residuals are the difference between the fitted values and the observed. So it's observed minus fitted equals residuals. And then here's sort of a summary of the algorithm that we went over before. I'm not going to belabor that because we've already been there. So let's move on to the exercise. Just to emphasize, you should all have a copy on your own Google Drive, or certainly a Google Drive that is not the, you know, the course Google Drive, a copy of this notebook. And the reason why I say that is that if you work with the, I don't even think you can modify our shared Google or our shared documents, but if you could, there would be a problem because then everybody would see your modifications. So you definitely want to work with your own. So here's what you need, here's what you want to do, and at least, you know, get started with the first one. And I want to sort of check in with you to see how this is going, because again, I know there's a wide range of computational skills. So here's the idea, just to get a warm up for parameter fitting. So you've got this linear pathway model, the one I just showed you up before, and actually just to emphasize this, let's see, actually, you know what I think I'm going to do is, let me show you this down below. Let's do over here, and I'll say this, getting started on item 1, so on the first one. Okay, so the first thing you want to do is be able to run that model, the linear pathway model. So let's say the usual one is we're going to create a roadrunner, and we're going to do a load A, or it's typically TE is, and then we have a load A. And then we're going to say, well, it's this variable here, linear pathway. And what it should do is it actually tell you what it is over here. So that gets me, that should actually load the roadrunner model. Let's see if it does. Okay, it looks like it did. Now, at this point, unfortunately, I've not assigned any values to, or I have a 0 value actually for all the kinetics constants. So if we look at roadrunner of like K1, okay, so if we do that, it's 0. So the first thing we're going to want to do is assign values here to be able to get what we think that, you know, how I generated the model. So I'll guarantee you these are the true values. So if we say that's equal to 1 and roadrunner of K2 equals 2 and roadrunner of K3, this gets boring, but we'll do one more, 3, and then roadrunner of K4 equals 4. Okay, so if we do that, and then we say, let's say that here's our data, we're going to run a simulation, is roadrunner.simulate, and then we're going to plot the data. Okay, so these are the true values when we use the parameters that I got here. But of course, the actual data that we have is this data over here. And we've seen what that looks like. That was this up here. So your job is to produce a plot that subtracts, let's say for this purple curve over here, this is S5, from these scatters over here, and produces a plot that shows for each of the species what the residuals is. So you actually have 5 plots, one for each species. Okay, that's the first step over here. What I think
does everyone know what a
is
residual is? Just for,
yeah, right. So to remind you again, the residuals are defined right here. So the observed value is going to be this one right here. Oh, actually, you know what I should probably do is let's show you how to get the observed and the fitted values. Okay, let's do that. Okay, yeah, that sounds like a good idea. Let me bring it up to that point. Good idea. Okay, so let's say, let's get you know what? Let me actually calculate the residual for S1. Let's go through and do that. So you see how that's done, and then you can do it for the other 5, and then, or the other 4, and then do the plot. So residual for S1. All right. So we know when we look at the data over here, and this is in the data frame form of it, we're actually going to, let me show you how this relates to the, if we look at the array form, which is what you're going to actually be working with. Okay, so if we look at this, you know, see, it's, let me go up to the top here. So in the array form, actually, you know what? Probably what makes more sense. Let me show you a slightly different form. This is the array form. But what you get when you run, well, actually, we have to deal with it. Okay, that's fine. We'll deal with this. So with the array form, what it is, it's a list. You see here this square bracket of lists. And so this first value over here this is all for the first row, and it corresponds to this row right here. You see the 1, 8.5, 0, 0, 0. And that's what's going on over here. 1, 8.5, 0, 0, 0, 0, and then 1.9, 1.09 is the second one over here. That first one there is time. This is time, and this here is time. And then at that, we see if for S1, it's 7.45. And that's what we'll see for the second row over here, 7.45. And so on. That's the way these data are structured. The way, Lucian, I assume there's been no discussion of arrays yet?
We had Herbert's introduction on the first day talked about arrays. Yeah. I don't think, and we talked about getting a slice of the array and that sort of thing.
Right, okay,
so a
slice of the array,
introduction, but yeah.
Okay, fine. So a slice of array we're familiar with. Okay, so you're familiar with how the arrays are structured. So if I say a linear pathway array, and I'm going to do a slice here. So a slice, I'm going to take all rows. Actually, you know what? I'm going to make it smaller than that just so we can see what's going on. I'm going to go 0 through 5, the first 5 rows. And I'm going to look at the 0th column. And remember, in Python, 0 is actually 1. Now, some computer languages do that. They start what's called zero origin indexing. So that's what Python does. So this is going to be time. So I'm going to put over here first. It's actually 5 rows of time. Okay, so if we look at that, and I see a syntax error, what did I do? Okay, I got a dot in there somehow, mysteriously. Okay, so that's what I've got here. I've got time is 1, then 1.09, 1.18, and so on. Those are my values of time. So the next thing I can do is, okay, so I'm going to do S1. So if I'm doing S1, then really what I want the same 5, but S1 is the first column. Or I'm sorry, it's the second column, and in Python indexing, it's index number 1. So if I do this, this is the value. So remember, it started at 8.5, then 7.4, and so on. That's the values there. So now I've got that. So this is, so what I'm going to call over here.
Don't forget to do your comment. It's first 5 rows of S1.
Yes, thank you.
Yeah.
Thank you. Lucian is good at keeping me honest. Okay, so what I'm actually going to do here, I'm going to change this a little bit, and I'm just going to call this, instead of the first 5, I'm going to do all of them over here, and I will change my comment too. So let's see, I'll call this just time, and I'll call this just S1. Okay, and I'm going to call this, since this is time, I'm going to give it a new variable. I'm going to just call it times. That's my values of time, and then this is going to be, I'll call it S1 S. S1's their values. Okay, so now I've got, oh, actually, you know what I want? I'm sorry, that's more important. This is observed S1s. So it's I generally make it plural if it's an array. Actually, what I generally do is for an array, I'll even say ARR. So this is actually will come across as array. If it's a list, I would use plural. So observed S1 array. Okay, so that's my observed. And remember what we're after over here is we're going to compute residuals, and residuals are observed minus fitted. We're after the S1 residuals. So that means we need the S1 observed minus the S1 fitted. Okay, so far so good. So I've got that. Now I ran a simulation right up here and I called that data. You know what? Let's call that fitted data. So it's more clear. We're going to be more specific. Fitted data. And we better change this too, or otherwise it will break when we run it again. Fitted data.
You can leave that out entirely and it'll use what it used last. Just plot with no arguments if you want.
Oh, plot with no arguments. Oh, we'll remember that?
Yeah, because it uses its stored data if you do that.
Oh, okay, fine. Great. Well, thank you. I just learned something too. I need to take the class. All right. Okay, so now we've got fitted data and we've got observed data. Okay, now the one thing that we don't have over here is I've got observed data for S1. I need fitted data for S1. So the question is, how do I get fitted data for S1? So the trick here, and I'm going to actually make a new cell to do this. If you haven't seen this already, if you just put the cursor down towards the bottom of the window, it'll give you a new cell. What I can do is take a look at fitted data. This is actually what comes out of the Tellurium simulation is a little bit more than a NumPy array. It's what's called a named array. It's somewhere between a NumPy array and a data frame. If you look at these things, just take a look at. I really recommend that you just do this kind of stuff. Just look at things, see what they come out as. You see, it actually names the chemical species. The chemical species are in square brackets. I believe that if instead you're using fluxes, I don't think they're not in square brackets.
The square brackets means concentrations. Without the brackets, it means amounts.
Oh, it means amount. Okay, fine.
By default, it's concentration.
In the naming. Yeah. Okay.
Yeah,
right. So the fluxes, since they're not normalized by volume, then it's an amount.
Yeah, exactly. Yeah, okay, it's just the species. By default, they come in brackets because it's the concentration.
Okay. I learned something again. I didn't know what the logic was there. So that certainly makes sense. So for the fitted data, actually what I'm after the fitted S1 data. Okay, and the neat thing about these named arrays is you can actually use the name at the top to be able to reference that array. Okay, so I can do something like this. Now, you have to be careful. You actually have to use the exact name. So if you put in S1, that will not work. You have to put in the square brackets because that's the name that's known there. Okay, well, that obviously didn't show me anything. But if I look at fitted S1 data, then what I'll come up with is that the one thing about these named array objects, which is a little bit annoying, is as soon as you slice it, what you get back is a NumPy array, not a named array. It doesn't preserve its own type. But in any case, so I couldn't do this again. But in any case, this is what I've got. So now I've got fitted data and I've got observed data. And so now to compute the residuals, we're just going to apply the formula from before. I can say, we'll call this residuals S1. And that's or actually it probably makes more sense to say S1 residuals. I usually like to use what's called camel case, where when you make a break in different words, you use a capital letter. And so that's going to be observed S1 array minus fitted S1. Oh, and I do not like that. I like to keep this consistent. Let's call this array. Yeah, this is sort of like, software engineering training about being very careful about names. So in any case. All right.
So
if we do this. Okay, so if we do this.
You have an equals?
I have an equals. I do.
There you go.
Yeah, that will actually. You know what? What I'm going to do is Lucian has already told you the problem, but let me show you what happens because it's very easy to make typographical errors in this stuff. It's so annoying. So rather than thinking that unfortunately the bulk of you will not have Lucian looking over your shoulder when you're coding, and I'm sorry you don't have that advantage. I'm glad that I do. But let me show you what happens when you do stuff like this. It ran. but you didn't get what you thought you got. So what you said was everything was equal to everything else. And so just to let you know that, you sort of have to figure these things out when you go back and look at it. And that's a common mistake. All right.
We're probably going to have to rerun everything because now you're going to get zeros.
Yes, it is. And that's another important point. You're in a notebook environment and it doesn't recognize some of these things. So now I've clobbered S1 residuals and observes S1. Yeah, right. Because what I did was I made observed S1 ARR equal to fitted S1 ARR. Hopefully you followed that. That was because of the mistake I made. Anyway, what I'm going to do down here is print this out. It's not going to be right yet because I've got to rerun observed. And I got observed from, I guess ultimately I guess observed was right here is where it was assigned. So I can just do that. And now if I look at the residuals, could not broadcast together. So I have something, okay, this is a good one. Okay, so I obviously have something with too much. Okay, so something is too long. So let's go back over here. Let's take a look at, okay, so let me first of all explain this error because it's useful. Obviously, I didn't intend to make this mistake, but now that I've made this mistake, it's useful to talk out loud about how you figure out what's going on because it's very frustrating, especially if you're new to what's happening here. So let's first of all interpret what's going on here. The operands could not broadcast together with shapes 151. Okay, so what this is saying in very computerese is that one of these arrays, probably the first one, has 100 entries, and the second one has 51. And because of those differences, they couldn't broadcast together. They couldn't
broadcast together in this case.
You can't subtract one from the other. And the issue is ultimately that how much data, the number of data values that I have in my observed is different from the number of data values I have in my fitted. That's the problem. So what I need to do is if we look at, and the way to look at this is if we look at the observed, let's see, the data frame would probably be the best way to look at this. If I, did I clobber that already? Oh, I think I must not have. Oh yeah, I think I just did. Okay, the issue is that if you look at the time span over which the fitted value of the observed values were calculated, let's take a look at the observed values here. I'll add a cell here and I say, let's do linear math with this. Okay, let's take a look at these. This is the data for that. And if you look at the bottom here, you see that the ending time is 10. And so it's doing its calculation over 10 seconds. And what happened here, which is not obvious at all because you don't see it over here, this is actually, you see it in the plot, it's only simulating over 5 seconds. So I actually have twice as much observed data as fitted data, and so it doesn't know how to align things. And what I need to do is if I make my fitted data go over 10 seconds. Oh, I'm sorry, you're right, 0. Again, unfortunately, you don't all have Lucian to guide you, but it gives you a feeling for what's going on here. Okay, so now when I do that, I get over 10 seconds. If I then here the observed, I've already done. You see that, and then here the fitted array. Let's see what we get. We should have, now we have twice as much data, and then when we go over here, oh, what did I not compute?
Yeah, it actually starts at 1. It's from 1 to 10.
Oh, you're right. It starts at 1. Thank you. So we actually should start this at 1. Thank you. Thank you for catching that. Okay. And then let's see here. I'll just go through and do all the cells. It's easier, sort of mindless. Okay. Let's see how we do here. Okay. So it's still what observed
and then
S1.
you can specify the number of points. So
yeah, the number of points should be consistent.
Well, that's exactly right. I'm just seeing where I made my mistake here with
in your call to simulate, you can change. You just told it when to stop, but you didn't tell it how many number of points.
Yeah.
Oh,
so 1,
okay, you're
10,
right.
Comma
right.
50.
Right.
I think is the number of.
I think I have 100.
Yeah, it's
Or
a
is
one.
that, or
Oh, you have
50, I
100
think.
original, or
I think
yeah.
it must be 50 because, to be the same.
No, no.
I forget which one
No,
is
it's
which.
100 actually.
It is
It's
100.
It is
100.
100. Okay.
Yep.
Let's do 100. I thought it was okay. Less. Okay. Let's do all the cells. Do that. Do that. Don't need that. Do this. Yeah. Okay. Right. And then we get more. All right. So now we've got the residuals. Thank you. But this was a great exercise because that error is a common error. That you don't have the same number of observations. The other thing to point out is that a lot of times you may need to do a little bit more work because your observational data needs to be time aligned with your fitted values. And so I generated observational data from the simulation, and so the times are computed in the same way. That may not be true with data that you have. You may have to do more work to find which ones align, right? Okay, so now we have residuals. You see residuals can be both positive, negative. These are the residuals for the for S1. And you see that they vary considerably. Initially there's some that are, well, this is, you have to put a decimal point in front of that because of the -1 over there. But you can see that towards the end, because ultimately S1 goes to 0, the residual is very small. All right. So it's 1:20 now. I would like you to sort of, all of you to get a chance to go through this. What you want to do is actually plot this. And presumably the plotting part is something you're already familiar with. The X will be time, and we calculated times up here. And the Y will be the residual. And then you do that for each of the species. Is there any other question at this point? Because I was going to give you about a little over 10 minutes to work on this. I saw that there was something that flashed up here with the chat. Let me look at the chat. Yes, right. Okay. Okay. So it's a lot of okay. Anything? I was just looking to see if there's some great detailed questions, but I'm looking more for the big questions if somebody is blocked right now with doing the exercise. So here's the exercise here, and I'm just talking about for right now. Let's just do part 1, and then or actually, I'm going to give you 15 minutes. Get as far as you can. I don't want to take too long. But do as far as you can, and then let's see, we'll come back together and sort of see where we are. Any questions before we stop for 15 minutes? Okay, so actually, maybe I should make it 20 minutes so it's a quarter to the hour. That's an easier thing to think about, a quarter to the hour. It gives you a chance for a break too. So a quarter to the hour, we will restart. All right, questions? All right. Be sure to share in chat, and I'll monitor my chat too. All right. Let me stop here. And great. Okay. See you in 20 minutes. So, if you have something, a value, an observed value at, let's say, time 1 and time 4, and you need to match it to something else that's at time 3, you might take, like a weighted, an average of the time 1 and time 4, weighting more towards the 4 because it's closer to 4. 3 is closer to 4. So there's a lot of detail around the time point discussion. Okay, so can people give me a feeling, either in the chat or by voice, how they did with the exercise? I mean, I'll go through that exercise so you get more of a sense of what I was looking for and what you come up with. How did folks do? Anybody offer?
If you want a minimal reply, you could do the reactions and do a thumbs up or an X.
Okay, right. That's a great idea. Okay, so yeah, maybe I could just, let's see here, view, gallery. Now I can see. Okay, yeah, if you folks could just give a thumbs up or thumbs down as to how it went. And your criteria for thumbs up are totally up to you. You know, you may have just gotten through the first one and that was just fine. You felt like you got something out of it. And thumbs down if you're frustrated, you feel like it was inadequate. Okay, I see some. I saw a couple of thumbs up. Yeah,
And there's an X there. I don't think there is a thumbs down, but
oh, there's an X. Okay, I haven't
an X,
seen
yeah.
the X. Okay, we did see an X from.
Yeah, from Anne.
From Anne. Okay, so Anne, if you feel comfortable, I would, you know, maybe you can make a comment where you, because it would be very helpful. There are a lot of people who are not responding. Again, you know, I don't want, it's not, I'm not going to hold you to account.
Your problems are not unique, and if you are up for sharing them, it would be helpful.
Yeah, we really appreciate it if you feel comfortable sharing.
Yeah, I'm fine with that actually. So I think I did part 1 successfully. So I have a scatter plot showing the residuals over time.
Great.
So
super.
Starting with a broader spread at time 0, diminishing to about 4 or 5, and after that it's pretty close to a clean straight line at 0. And then I got stuck figuring out the for loop of part 2. So I'm trying to step through different values of K1 and haven't quite plotted that in a way that feels accurate.
Okay, fine. And again, Anne, I don't know what have you had much experience with Python before?
Mostly R. So I'm not a complete novice when it comes to coding, but pretty much a novice with Python. Okay,
fine. So that's a lot to struggle with too. And I realize that's, sort of a challenge as well. But I'm sure, I know that there are some folks from, looking at the early introductions who had no programming experience. So I imagine for them, it was a considerable challenge. Okay, well, let me go through this. I'll go through this briefly on how I approached it. And I use this as a way of sort of, giving answer to the question, but, some of you will find it, will maybe take a little bit longer to study it than others because of, prior experience. Okay. I have to find there it is. Okay, so if I go here to the exercises, and okay, so of course I have to rerun everything. It should go quickly. Okay, so here are the exercises. So this is the notebook that says exercises and solutions. You all have access to this, so hopefully this is sufficiently descriptive. And I apologize in advance if some of this, I think you did have some background in dictionaries. You've seen that already. So
at least a very little bit, but yeah.
Very little bit. Okay, so what I'm giving you is, also will help you maybe a little bit with some of your Python exposure as well. So a dictionary is a kind of data structure that provides sort of an associated memory. It tells you, instead of referencing something with a number like column 1, you can give a name. So I created a dictionary for the true values of the parameters. So this is for the parameter K1, it has a value 1. So you see that this is actually a string, it's in quotes. The other thing to notice is with a dictionary, you have these curly braces. That tells you that it's in Python, it's that data type. You have to begin and end with those curly braces. And then this says the value of K1 is 1, 2, 2, and so on. So here, you're familiar with this, do the simulation with the model. So now I have the Roadrunner object. And now what I'm doing is I'm assigning the values that are the true values, I told you, 1, 2, 3, 4, to the names in Roadrunner. So Roadrunner, the name is, at this case, is
Ease
going
is
to
a new
be,
concept to everyone, or at
okay,
least to the
gotcha.
Python
So a
newbies, yeah.
dictionary is structured into what are called keys and values. So this is actually a key, and this is its value. And similarly, this is a key, and this is its value. So when you say keys plural over here, what it's doing is it's giving you a list of K1, K2, K3, K4. So when I say RR of K1, that's get RR of name. This is a loop. We'll go through all these keys in sequence, and the first one will be K1. So RR of K1 is going to be equal to parameter dict of K1. So I say get parameter dict of K1, it then yields its value. So that's a way, basically a fast way of assigning to the Roadrunner object, assigning the values to these various parameters. I do the simulate over here with the correct range and count, like we went through before. I sort of struggled with in the when we're doing this together on the exercise. And then you get to see here what the so this is, remember from slicing, we get an array when we look at this model array. And so this is the first 10 rows, and it's giving me all columns. So these are the columns and the data that I got out of the result of that simulation. So this gives me now the results for the model part, or the fitted array. And then these are the observed values. So we saw that from before. And now I'm computing the residuals. And the nice thing about arrays is you can basically do arithmetic on arrays just like you would with scalars. So this is actually subtracting all cells, columns in the observed from all cells, columns in the fitted. Now you remember that the first column is actually time. So we have to get rid of time. Time we don't really want from this.
You use the term scalar. Scalar is a fancy term for a number, basically. In
number,
this context.
Yes. Yeah. Okay, thank you. It reminds me of, sort of like a simultaneous translation that's going on here. Okay.
Yeah. Translated to newbie speak, yeah.
Right, yeah, translated or maybe to human speak. Okay, so by doing this subtraction, what we've done is, since these are aligned to the same time values, that first column, which is time, we're going to subtract the same value in one column for the same value in the other column. Obviously, we have it with zeros. So if we want the actual time value, we have to recover that. And that's what's going down happening over here. And now if we look at the residuals, we actually have the values. We have a good time value over here. Then here are the residuals for the other, for the 5 species. Okay, so this whole process of doing this calculation is encapsulated in this function over here. And I assume that you have not had an introduction to Python functions. Is that correct?
We actually did get a brief introduction to functions.
A brief introduction to Python
I don't know
functions.
if they've ever, I don't know if they haven't ever been asked to use one of them, but they were introduced as a concept.
Okay, so functions play a critical role when you're writing and when you're doing any sort of computational analysis, because functions will encapsulate your workflow, what you've done. And much like in a wet lab where you want to have a notebook that captures exactly the sequence, doing it in an experiment, functions to some degree for computational work, are sort of like a computational notebook. It records exactly what it is you've done, allows you to repeat the same thing over and over again. And that's what's going on here. So with a function, you give it arguments, which are things that are used internally over here. So this is the string representation of the model. So like it's an antimony model, the observed values as an array, the parameter dictionary, like I showed you above, the start time and the end time that you're going to run the simulation. And this is doing exactly what you saw above, but inside a function so that it becomes repeatable. And now we can use this function over and over again. So like what we saw over there, calculating those residuals, we were able to do it now. We can specify just the model, the array, and the parameter dictionary. The one thing I show you over here, which is a little bit of a subtlety, is you see that these are just single names over here of variables and comma. These ones over here are a little different. They have an equal after them. And these are what are called optional keywords. So these are values passed to the function, but they have a default setting to them. If you don't say anything, the default setting is 1, the default setting is 10. That's extremely useful when you want to enhance the capability of your workflow so that you add additional considerations. You can make it so that the default value works fine, but now I can change the start time or I can change the end time. Okay, then over here, this is a script. So this is not a function. There's no, a function begins with def, and then you'll see a colon there, and then everything is indented. That's a function. But if there's no def and everything is to the left margin, this is a script. It's just a sequence of steps then that get executed. And the core part here that Anne was sort of trying to deal with was to deal with the iteration that goes through as you try and plot everything. So we have previously calculated this model array. Okay, so model array comes out of the simulation. It has the names of the columns. You could specify, actually, to make this a little easier to understand, why don't we just say column names over here? And we're going to do S1, and they should be square brackets. S1. I'm trying to take advantage of the data structure that comes out of Tellurium, which includes the column names. But that may be a little bit confusing for some. There's a lot that's going on there. And instead of doing all of this over here, I'm just going to say column name so you get to see it directly. You don't have to look for some abstraction. This is a little bit fancier, and I apologize for this. So you can, if I just said for name in column names, it would give me the name of the column. But I want both the name of the column and its position in this list over here. And that's what this enumerate does. So I get back, for example, on the first step of the iteration, it will give me index will be 0 because I'm in the 0th or first element over here. And then name will be N1. And the second time I go through the loop, it'll be 1 and S2 and so on. That's what's going on over there. This is what I'm doing here is I'm plotting the plots in 2 dimensions to sort of save space. So that's why it looks a little bit fancier. That's the use of this subplot capability over here. But the core part of it, you can ignore that fanciness and just do, in sequence. The core part of this over here is then the scatter plot. So I'm doing, we've already calculated the residuals. It's just a subtraction. We say for the time and the residuals, do the plot. And then I title the plot. And that's all that's going on there. So there is a little bit of extra stuff in here that I included intentionally for those who are interested in furthering their Python skills. But hopefully the core part about this, the iteration part, and then doing the plot is something that you can just extract in itself, and you don't have to do the things that involve a little bit more detail. And then here's the kind of thing that you see. And one question that comes up is that we see a lot of variability in these residuals early on with S1 and later on with S5. And that should make sense based on when you look at the data itself. Remember that the observed data were calculated as an error fraction of the, or a fraction of the true values. And so if you have large true values, which you will, and when S1 begins, because all the math starts there, and at the end for S5, you will get larger variability in the synthesized observed values. And so the residuals will also vary more. And that's what's going on there. Does that make sense for folks? Let's just sort of focus on this first exercise. Any questions on this? Okay, so I'm not going to, I'll talk a little bit about the second and third one. I don't want to spend too much time. We only have an hour, and I want to make sure I at least talk briefly about optimization and in more detail about the workflow for actually doing parameter fitting. So Anne's question was about this loop, about how do you evaluate possible values. And let me go through this because this is a useful thing, you know, to be able to extend your Python capabilities so that you can write loops comfortably. So what I did here is this is how I'm going to explore different values of a kinetic parameter. Remember, the kinetic parameter we're going to look at is K1. Its true value is 1. And then what I'm going to do is be able to I initialize this to something that has a range from, and there are various different ways you can do this, but has a range from 0 to something I think it's going to be close to 4 there. And that's what that statement there does. I want to be able to store the results when I do a simulation and I look at what the residual sum of square is, you know, the sum of the residual square. So I'm creating a dictionary, one of these associative memories. And the key for this dictionary is going to be the value of K that I chose. So it's going to be from, so if I run this, I guess I've already run it. So if I take a look, I'll show you what that looks like. This is a great way to understand codes too, is to run them and then just look at what stuff looks like. So if we look at this K values thing here, this is what it looks like. Here are the different values. You see it starts at 0, it goes to 4, and it goes up in increments of 0.2. And you can sort of see that that's what's going on over here. It's going up in increments of 0.2. Okay, so in this loop, here's what's going on. So when I say for K1 val in K1 in K, I guess I called in K vals. I probably should have been calling it K1 vals to be, I like that better. I'm going to call it K1. K, I'm not sure where that went. That went in the wrong place. Yeah, get sort of anal about names sometimes. Yeah, K1 vals. Because the point is, this is a set of values and this is one value within it. Let me just run that again. So that's what we've got. Okay, so for each one of these values in this list over here, which we just saw before, here's what I'm going to do. I'm going to make a copy of the set of true parameters. So this was that parameter underscore dict that had all the true values. See, I think, yeah, it shows actually, oh, that's great. It shows it all. So that's the parameter dict that shows all the true values. So that makes a copy of it. You don't want to just assign it. Go ahead.
Like in Python, it's not usually a copy. Oh, I guess it is. If it's just a value, then it's not a copy, right?
Right. So in this case, and what Lucian is alluding to is Python is a little bit tricky as to when something is a value and when it's the address of a value. You know, and it's a little bit difficult. If I were to say instead parameter dict, or lowercase parameter dict equals uppercase parameter dict, and then I modified this, it would actually change this one here because it now points to the same address, and it would manipulate the same way. But when I say this, it
address
actually
means like place in memory where it actually stores the data. Yeah.
Right. And when I do this, it actually makes a copy of it at a different place in memory. So I'm not destroying the original one. So that's what's going on there. Then that's a little bit of a gotcha with Python. I mean, every language has its gotchas, but that's a little, and you have to sort of know when you need to do this and when you don't. So typically with any structure, with what are called the element, the basic values, like a real, a float, a string, you don't have to do this. But anything that's a structure, a list, a dictionary, or anything more complicated, you need to do this copy kind of thing, this kind of recreate the structure. So now that I have a copy of it that is not the original, I can modify it. So this is my dictionary. It's associative memory. I've got the name of the parameter, for example, K1, whatever the value is. And remember this dictionary that this dictionary here has, is working with the name. So my parameter name, I'm just working with one parameter over here, K1. I could have put in just K1 here. The reason why I did it this way was so that it'd be easy to explore if you wanted to do K2 or some other parameter. So I put in, K1 equals this particular value, which I'm getting out of the loop. And then I calculate the residuals. You have to go back to this function over here. That's why I created a function, so I could do it repeatedly. But it's the same thing that we saw in that script, where you run the model, then you do the subtraction, and then you calculate the residual sum of squares. And then I assign.
I may have missed it, but did you assign things to the other values of K1?
I did not. I'm keeping everything else constant.
The other K2 and stuff, because I thought
K2
at one point
is
they were
unassigned,
initialized
right.
to 0. Yeah.
No, well, yeah, no, those were initialized when I did the simulation.
Okay, got it.
Yeah, the simulation does that. That's actually in this calculate residuals. It makes sure that all those are assigned to in the default setting for this thing is, well, it comes to, this is one of the parameters. What's being passed is that original set of parameters with only K1 modified. And so when I do this assignment over here, it's assigning all of the parameters of the model are getting assigned.
So that's a little bit of a cheat, because then all the other values, all the K2, K3, K4 are all accurate in this case.
Absolutely.
So
I mean, you can look at it as a cheat.
Yeah.
I wasn't claiming that this was parameter fitting.
No,
Yeah, right. This is about seeing the effect of varying the parameter.
Right.
That's all.
Right.
That's all.
Okay, got it.
Yeah, that's it. Okay. And then I save the result over here in the request dictionary. Okay, so that's what's going on here. Okay, so this does the calculation. Then at this point, I have the request dictionary. We can see now what the results are. So we see that now we know the true value is 1. And we're looking at this is a value of K that we chose. This was actually the one that was in the original model. And if we ran the simulation and then calculate residuals and compared the residuals with the R-square, and did the R-square calculation, we'd end up with a residual of 19,086 approximately and change. But if instead we use a parameter value for K2 of 0.2, we're down to 65,000 and so on. And you see that when we get to 1, we're at 3818. Now that is not 0, right? It's lower than 19,000, but it is not 0. And further, once we go to 1.2, which I guess this is 1.2 with a lot of zeros in the 2, then we're at 38,027. So clearly this is the low point. And as we saw before, this is actually turns out to be a convex surface. So you can actually do this whole gradient descent thing. And it works, which is a rarity, but it works in this particular case. So this is actually the true value, but it's not 0. And the reason why it's not 0 is we've introduced randomness into the observed data. And obviously there's the true value has no randomness in it, so we don't come up with this, exactly 0 for the R-squared, but it is the smallest value. And then you can see now the other thing which is sort of interesting here is the way, and I'll show you this actually in the next slide. So we can plot this stuff. Hopefully the plots are pretty straightforward for you at this point. You've seen plots before. You can plot the this is just showing you that, okay, so let me describe what's going on here a little bit. Let me just show you this one so you get a feeling for what's happening here. So here's a plot. This is basically the values of K1, and this is the R-squareds over here. So what am I doing over here? What's this list of requestDict.keys? What is that all about? Okay, so remember the way this requestDict is structured is that this is pairs of the setting of the parameter and the R-squared. If I say .keys, what I'll do is I'll just end up with the stuff to the left of the colon. So that's all this. These are the keys over here. But, and this is, a lot of what you end up doing with any sort of programming. This is not a data structure that the plot function will accept. It will not accept a keys data type. So you have to convert the data type. and this is a lot of times the common problem you run into a list. And so now if I say list of this, it gives me a data type, which is a list, and then the plot function will accept it. And a similar thing with the values. The values are the R squareds. So this is just basically a plot. I'm putting on some labels. I gave it a title, and here's what I ended up with. So this pretty much gives you the same qualitative feel. Start out with a very high R squared. The R squared is lowest at 1, but it's a little bit hard to see in the plot. I mean, we could see that when we looked at the actual data, but it's a little bit hard to see in the plot because then the ramp up from here is very, very slow. And this is another characteristic of these data and this model, and that is that where you come up with for the smallest value, there's a little bit of fuzziness. Some things, especially with depending on the nature of your data, you may find it somewhat flat. And in these cases, the models are less what's called identifiable. You can't necessarily do quite as well with getting the exact value for the parameter. And that's a characteristic or a challenge that you face inevitably in parameter fitting. So let me pause here and see what questions there might be. I'm not going to go through as much detail in the third part because I do want to get on to these other parts of the talk. Any questions?
I think most things in the chat have been answered. So.
Okay, great. So then let's just go. So the third part was to come up with a simple fitting algorithm. And this I really leave as an exercise to those who have had or want to develop more of some programming skills. Here's a sort of simple approach that you might do for exploring a range of values. Basically, this is the exhaustive search algorithm that you saw from before. And it shows you how you might actually construct this and the challenges associated with it, as we described before, because there are a lot of space to explore. All right, so I'm going to spend just a few minutes on the optimization algorithm section. I want to spend the bulk of the remaining time we have on the actual example of parameter fitting. So let me go through here. I'll bring up the optimization notebook. And I want to make sure the concepts are clear, because for those of you who would likely be using a tool like SB-Stoat or Copazi, I think has tools for fitting as well. Now, I want you to just understand what's going on under the covers so you can better interpret the results that you get. And the optimization algorithm and the limitations of it is core to this. And this really is all about the fact that if you don't have a convex surface, which is absolutely most of the time, then the optimization algorithm is finding what we pointed out before, Lucian pointed out, is what's called a local minima. That means locally you're at the lowest level. You're like a valley and a mountain. That doesn't mean you're at the bottom of the mountain. That just means you're in a valley. And to actually find the bottom of the mountain, you might actually have to climb up a little bit and climb down some more to actually find the bottom of the mountain. And that's the challenge with any of these optimization algorithms, made worse by the fact that you're dealing with a large, high dimensional space, a lot of parameters that you're exploring simultaneously. Okay, so these are the preliminaries. It's the same as in the other notebook. I'm not going to show this in details. So here's the framework and the context for optimization algorithm. What you're doing with an optimization algorithm is you're saying, I have a function of a whole bunch of variables. In our case, the variables will be parameters. I realize we have species, floating species that are there too. If we're worried about an initial concentration of a floating species, that would be another parameter. But for right now, I'm going to just say that this is a function of the parameters, and we have, whatever the other parts of the model we feel comfortable with in terms of, starting values for species, for example. What I'm looking for, this is a function of these parameters. I'm looking for some value of these parameters that minimizes this function. And that's really the whole point of the optimization. So what the notebook does, and again, I'm going to leave this for you to look at separately, depending on your interest, gives you a simple example of what optimization might be like if maybe your optimization is about how close am I to a particular point on the plane. Again, this is nice because it's very graphical. You can see this here. Here, the smallest value is very dark. So depending on how close I am to this point, I get darker if I get closer in. And we go back to show you, remind you about convex curves. And then non-convex curves. Here's a great example of a non-convex curve where there are a lot of little valleys, but they're not at the bottom of the mountain. And you can get stuck in those little valleys. And then the last part here, which is probably the most relevant for those who want a lot of more technical detail, is how do you actually use some Python libraries to do the search for the minimum value or the optimum. So this uses as its example for finding a minimum value, this distance function. So typically the structure of these codes are you write a function that computes a value, basically a residual. How close are you to the best? So in the case of our simulations, we might compute like an R² value for a value for the sum of squares of the residuals, and a smaller value is better. And what the optimization algorithm will do is it will run that function over and over again until it finds that you were at the actual minimum value. So here is one example of this. The function is named distance. You can add some constraints to it. You tell it where to start. This particular function here, this minimize function here, it's going to actually use gradient descent. So good thing to try if it's fast. See, try your luck. Who knows? You may win the lottery. So that would be one approach. If you want something that's going to do more than gradient descent and deal with these non-convex surfaces that are so common, you probably would like to use another search algorithm, and differential evolution is one example of that. It's one that we use very commonly. It's slower, but it does a surprisingly good job of finding a minimum value on a non-convex surface. And again, it has a similar kind of structure here. You specify the function that you're trying to minimize, and then you can specify with differential evolution, you specify what are the limits on the values of the parameters. And so that's what you do in the bound. So that's why this is structured. There's an exercise here again for those who are interested, and the solutions are in that exercise and solutions notebook. So I know I went through that very quickly, but what questions do we have? I'll look in the chat, see what.
Hello, might I ask a question, but I'm not sure whether it's the right moment to ask this question. I was about to ask the question in Slack, but I think that it's more efficient when we talk. My question was about the multi-objective optimization. When you have not only one function, but you have several, like, okay, 2 or 3 objective functions. And then you might end up with a different set or several sets of parameters that fit the data, or you reach the minimum of the residuals that you aim to. And then you might need to choose among the sets of parameters, which is the good one, but they all fit the data that you have used as an input. So how do you deal with that?
So actually, I mean, this is a great question. And there are a few parts to this. First of all, it's important to separate, and this is in no way, ignoring that there could be multiple objectives, but many times instead of multiple objectives, what you have are multiple constraints and a single objective. If you can phrase it that way, I mean, a constraint would be like the parameter has to be greater than 0, or I know physiologically, this constant has to be less than 100. Those would be examples of constraints. And those are readily accommodated by these optimization algorithms. So typically the bounds will do that. Constraints are sometimes called hard objectives. They have to be satisfied. You do not have a solution at all. It's infeasible is the term that's used if the constraint is not satisfied. Whereas the objective is what's called a soft, is something that's more soft in that you're trying for the best, but it may be pretty high. So just to clarify with you, you're talking about truly multiple soft objectives as opposed to some hard constraints in a single objective.
I guess yes.
Okay, fine. So and there are examples of this that you may look for something that is close on many ways. So there are many different ways to deal with this. Mathematically, a common way to deal with this is you have some meta objective that weights the other soft objectives, like this one times 0.2, this one times 0.5, and so on. You can do that. Another possibility is what I think you alluded to, is that you calculate, several optimizations under the different objectives, and you do some sort of analysis maybe that makes more sense in terms of your scientific question and your understanding of the constraints involved. And that's another perfectly valid approach to it. So, but I think, one of the first steps is just to, make sure that there's clarity on when you're actually talking about something that is an objective versus a constraint, because those constraints are dealt with differently. So.
I could say another thing that you can do there, you were talking about like, what do I do if I have two different parameter sets that both fit the data reasonably well? Yeah. And one thing you can do is called data, or it's model-driven data collection. Basically, you set up your model with those two different sets of parameters, and you try to find some condition where they would predict wildly different results. And then you go collect the data in those conditions. And then that will distinguish between your two parameter sets. You can do that for the model as well, right? You can say like, here's a simple model and here's a more complicated model. Can I distinguish between them? You answer that by saying like, can I figure out a set of conditions under which they predict very different things? And then can I go into the lab and actually collect that data under those conditions and see which one it must be?
I understand. It can be kind of challenging when you have not only two sets of parameters, but you might have like a Pareto front that represents all the sets of parameters that fit the data. And
yes.
And then it becomes kind of subjective to choose among all these set of parameters that are selected.
Another thing you can do is to see if you can rephrase the question that you're after to not depend on the particular parameter sets. So like all models are there to help you answer some question. And if the answer to that question might be the same under both parameter sets, or it might set some constraints, you might not know the exact answer, but you might know more clearly what the answer must lie inside sort of the bounds of that answer or something. So yeah, like knowing what the uncertainty is can itself sort of be an answer to those sorts of things.
It just sort of a brief addendum to Lucien's responses, which I think are really good, is that you could find that when you search for this situation in which the two models predict different results, even though you have the parameters are very different. So you expect, on some circumstances, they predict something different. There may be circumstances in which you have a hard time finding that, situation in which they predict something different. They may predict pretty much the same, in which case you probably have a situation where parameters are not identifiable. You don't have enough detail or enough data to be able to make the distinction. And that's something else, and that's really going back to your model and figuring out, what can I do differently? Most likely reduce the number of parameters so that
parameter reduction is definitely another thing you can do. Like if two parameters sort of, as this one goes up, the other one goes down, and you don't know which, then you just make a new parameter that is the ratio, and then apply that to your math, and then you at least you know what the ratio is, even if you don't know specifically what what the difference is between the two, what specifically each value would have been.
Mm-hmm.
We have one more
Hopefully
question.
that's helpful. Go ahead.
How does differential evolution help like make things faster? Like if you were to do an exhaustive search and it would take 20 years, how on earth do you reduce that time by like
Okay.
What is this magic?
Right. What is this magic? Well, first of all, there's no free lunch here. The reason why it takes less time is it is just one way to go about it. I mean, it's not, you're not going to find the best answer necessarily, but you are going to find a answer, and it'll just take less time. And it avoids it doesn't follow much like, well, gradient descent. I think you probably all have a feeling for that. You're just trying to go down the hill. Okay, so that's one kind of heuristic. It turns out to be the best thing to do if it's convex, but it's just really heuristic in general. But you could have other heuristics, and that's what differential evolution is. What it does is it has this whole metaphor associated with like biological evolution. And the idea is that you go through rounds of solutions where you sort of take some of the best and combine them together in some way and then generate a new round. It's a heuristic. There's no reason why this should work well, but it just happens to. And depending on how many rounds you do and the nature of some of the details of the algorithm, it can take less time. But it's certainly not something that would find you the correct, the absolute best solution, which exhaustive search would, but exhaustive search is impossible. It's intractable.
I think basically what's going on under the hood is that like one local minimum shares some characteristics with the global minimum. So you find a local minimum, you save everything about it, and then you sort of try swapping out a few things with it. You are doing far leaps from that local minimum, but you keep some characteristics. Like maybe K2, K3, and K4 are pretty close, but K1 is way off. But if you change K1 enough, you go sort of up the hill and then back down, and now K2, 3, and K4 with this new value of K1 is better than it was. And that's the hope. There's no, I mean, there's nothing inherent in things that we know of that will tell you this is definitely going to work, but often it seems to. So there does seem to be, basically it's exploiting hidden patterns in your in the space of your search space.
Well, that's a good description. Any other questions? Okay, well, let's go on to this parameter fitting part 3. The purpose of this part is up to this point, really the focus was on what is parameter fitting and what are sort of the parts technically that you have to do. Now this is actually about doing parameter fitting. And the reason why all the background was provided was so that when you apply this, you get a feeling for what's going on under the covers. So there's a tool that I developed called SB-STOTE. The name comes, but we had this philosophy, we're going to name things after animals because we want, we're developing a bunch of tools for SB as systems biology, and STOTE is an animal that sort of searches for things. So that seemed like it was a little reasonable analogy. And what it does is allows you in a command line setting to use Tellurium to try and find values of parameters with some controls. So you can do this interactively. So I'm going to introduce you to how this works. And so the exercise here, which hopefully we'll have a little time for, so you can get a feeling for what using it, will be to apply this to the wolf model. The example I'm going to use here, the running example, is going to be this linear pathway that we saw before. So the minimal input information that you need to do parameter fitting is you need the model. It's like an antimony model. You need observational data, And then you need to know the parameters you're supposed to fit. I mean, I guess by default, you could say fit all parameters in the model, but some of those may be technically constants that, you know, are set by, you know, for biological purposes, or, you know, you could have a constant, I guess pi is a constant too in Tellurium. You're not gonna, you know, search for the right, you know, value of pi. So that's why it's good to express that explicitly. So here are the inputs, the model, observational data, and then the specification of the parameters. Now, what we do is you, much like with what you saw with differential evolution, it makes sense to specify bounds on the parameters too, you know, because otherwise you're searching in areas which may not make any sense. So, so here would be for the linear pathway. We know that the true values are 1, 2, 3, 4, corresponding to K1 through K4. And then you specify the input parameters with lower, you know, where you're going to start. That's the value there. This is the start value, and what the upper one is. So it's actually, you know, in terms of parameters, estimation or parameter fitting, this obviously becomes an opportunity to, you know, do some interaction, because depending on the range that I specify, if I specify a range that's too wide, you know, if I specify this as 1,000, for example, or something like that, it may be that my search takes a very long time. If I specify it as too narrow, I may end up not finding something that's a reasonable value for the parameter. I may end up with residuals that are far too large. And similarly, where do I start in the search space? We saw that when we looked at the surfaces, that, you know, I may be, you know, nearby, you know, a valley, and I'll go down in that valley and never get out. So all those are things that may want to be able to adjust and play with over time. Okay, so in our case, the names of the columns in the data are this. Okay, I guess I've run all this already, but let's see here. So if I run the model, which I guess this has already been run, here's an example of if I look at, so the name of the, if you install SBStote, you're going to use a class called model fitter. Right now, this is all done by using their examples that you'll see in the web page, and points you to a notebook that uses this. But if you look at this, you know, description of it, this is the main starting point for this. You create an object called a model fitter object, and then it has various arguments. Let's see if I make this a little bit wider. So you can see it's various arguments. You can these are all in the form of like most of them in the form of keywords. You can specify an end time. There are various ways to specify the model. You could use Roadrunner or otherwise, the observational data, and so on. Let me show you the sort of the simplest example over here. So we're going to specify, say, the model first, and then you give the data. This is in a particular format here. There are various different ways you can do this, but if you've gotten array data, like what we have with linear pathway, you have to specify the names of the columns and the array, and this is something called a name time series. So you just, you know, use it like that. This would be a very common thing to do. If this turns out to be a comma separated variable file, you could just put the path to the file in here as a string, and that will work too. And then the parameters to fit, and we saw that from before, that is K1 through K4. So, so that's the way you set this up, and you can run it. So I'll just run it again here. Okay, so it ran. And then let's see here. If I clear output, so you can see it actually does something. Okay, so now if I show the results of the fit, so here's the information you get out. You get the estimates for the parameters. So this is pretty good, but you know, the linear pathway model, I would say if a fitting algorithm can't fit this one, just throw it away. This is such, you know, low-hanging fruit here because it's a convex surface. So if you can't fit a convex surface, you know, fine, you just go home. So, but this is the information you get. You get the K1 through K4. And you get some other things that are interesting here. So this fit by default used least squares. When we talked about least squares is one of these gradient descent methods. It also tells you how many times it had to do an evaluation, basically a simulation. in order to find these values. And that's what a number of function values is. It only had to do 6. That's really small. That's very fast convergence to it. And this is another one that's useful over here, the chi-square value. Chi-square is basically like an R squared. And so the absolute value doesn't mean much, but when you're comparing fits, looking at the chi-squared value is very useful to get a sense of how good it is. So this fitting report is helpful. I mean, we already know what the right answer is, so we know these are good answers, but it's interesting to see some of these other measures. When we don't know the right answer, we can look at like number of function evaluations and the chi-square, these for comparisons. The other thing that's extremely useful is SPStope provides, let me get rid of this so you can see more. SPStope provides a number of plots that you can do, and probably the most useful plot I found is this fit all. And what fit all does is it plots the observed values to the fitted values. Now, obviously, the difference between these two is the residuals, and you can see the residuals, but it doesn't put it in context, because you might have large residuals, but that's okay because the values are even larger. It sort of gives you more of a sense of what's going on. Also, it tells you more. You get more of a feeling of what's going on with the underlying model at the times when values are skewed. So S1 looks like it's really good. S2, we have some interesting things here with some of the values popping up over there and over here. S4, you get a little variability. And S5, we saw from before that we got a lot of variability. Now, one of the things that's a little bit problematic here, and you can change this with the plotting package, is the scales are different. This goes from 0 to 12. These are much smaller. These are like 0 to 3. 1. So, the deviations over here are actually quite modest over here. I mean, this is very small deviations, whereas the deviations over here are significant. So if you were, in the real world, if you didn't know what the true fitted values were, this might be a little bit more troubling. But then if you look at the observed data, you may say, well, yeah, I've got a lot of variability there anyway, so it's not so bad. There are a variety of other plots that are available with SPStope that you sometimes can consider useful. They're sort of packaged in this method over here called plot residuals all. And you get a lot of different stuff. So this is the autocorrelations, you'll see, to see whether or not there are relationships between values of residuals at different times. This is sometimes helpful in terms of us understanding if there is some other structure that's present in the model. You can look at the distribution of residuals, again, which can be helpful. I mean, some of this is sort of obvious when you see the spread. These are fairly tight distributions. Obviously for S5, it's not particularly tight. And there are, this is correlations, separate correlations. So there's a variety of plots that you can get. But to be honest, the workflow that I generally use is I'm going to do some kind of a fit. I'm going to look at the fit report because I want to see the chi-square. I want to see the number of function evaluations that are being done. I want to look at this over here and see, sort of qualitative what's happening. And then I'll change something. And typically what I'm changing is I'm going to change maybe the range that we saw up here. So these are things I can change. I can change this range and change where I start. And the other thing which can be very important to change is the fitting algorithm. I can change the fitting algorithm. So let's do an example of this. Go past all this stuff here. So workflow for linear path fitting. You know what? It's 20 till. Rather than doing this one for the linear path, I think what I'll do is there's really probably not enough time for you folks to do the exercise, which are welcome to look at separately. But I think what I'll do is I'll go over the wolf exercise with you so you get more of a feeling for something, because the linear pathway is not terribly exciting. The wolf one is a lot more interesting. Let's see, I probably have to run this again. Make sure that runs okay. Say failed, I'm not sure why. Okay, this is running. All right, so let's get started on this. All right. So this is the wolf model in entirety. This is what you get if you know, this variable wolf underscore model is available to you in the notebook. If you print it out, you get to see the full antimony model. And these are the parameters that we're looking at over here. And wolf underscore data, I think, underscore ARR, I think that's the one, is going to be, I will see it down here. Yeah, I want to make sure I've got that right. Just looking for the fitted data because I do fit. Yeah, this should be it. Okay, all right. Yeah, wolf underscore ARR is the data. Okay, so I mentioned before about parameters, about encapsulating a workflow. And this is both so that it's easy for others to recreate what you've done, as well as for you to do this sort of interactive exploration. And typically, I'll create a function for whatever model I'm looking at. I'll create a function called doFit. And what doFit does, it does, you know, includes, you know, options for whatever else, whatever I want to change. Like, for example, I want to change the end time, or I want to change the fitter method, or maybe I want to change something about the parameter bounds. I'll do that to, you know, be able to have some flexibility. And then what doFit does is it encapsulates all the steps I want. So I'm going to, just like we talked about before, you know, we want to be able to construct, to do a fit for a particular setting of parameters. So a fit involves one of these optimization algorithms. You have to give it the model, you give it observed data, you give it, you know, how you're going to, the algorithms for fitting, that's what this is. And then the parameters to fit includes the information about not only the parameter names, but also the bounds, lower and upper limits, as well as the starting point. So those are all things I want to change when I'm doing this interactive exploration. Is test over here is because, and I didn't go into any of this in some detail, you know, when you're doing this kind of computational research, it is really important to make sure that what you're doing is reproducible. It is so easy to make mistakes. And hopefully, you know, from all the corrections you've heard from Lucien and other students on this call, you see, very easy for someone who's literally spent his entire career in the computing industry to make a lot of mistakes. Yeah, very easy. So it's very important to have tests. And you'll see at the end of all of my codes that I will have something called tests. Well, I will actually run the function. It'll actually be part of the cell where the function is defined, just to make sure that I, you know, get something that's not unreasonable. These are just what are called unit tests in the software industry. The other thing which is critically important about whenever you have a function that you're going to rely on is you say something about what you're doing. In this case, it's very brief. I'm fitting the wolf model. Also, what are the inputs and what are the outputs? And the key thing about the inputs and the outputs is know what the data types are. We ran into this before, that you get, things break typically in codes because you have the wrong data type. I mean, there are other reasons why they break, but that's a really common one. So just to tell someone what they're looking for, like the end time, actually, technically, it's not an integer. It actually technically is a float. It's not an integer. The fitter method, so this is a list of strings. So an example would be least squares. That gives us gradient descent. Differential evolution is another fitter method. And then how you specify the parameters. And that's one of the, you know, as I showed you up above with the lower bound, the upper bound, and then the setting of value as the starting point. And then this encapsulates method, pretty much like what we saw before. Not only does it run the fitter, it also does a plot. And you'll notice here that is task comes in here because when I make changes to the cell, you know, I don't want to see a plot out of here. If I change this to, you know, is test, then it would actually show me a plot. Okay, so given this background and then that sort of function that encapsulates the characteristics of the model, here's what I want to do. I want to be able to see how well I can fit the wolf data. Now, what I can do, let's start out here. What are the parameters as I've got them over here? Okay, so what I chose is these are the parameters for the wolf model. So I've got, I guess, 16 right here. And what I've done over here in the comments is I've shown these are the true values. So the true value is 550, 1, and so on. These data are synthetic data. They were generated in the same way as I did with the linear model. We added a little bit of random noise in there. And I specify a lower value, a starting value, and then an upper value. I change the different, I mean, you can see some of these upper values are quite large, like 76,000. So, you know, to make it so that, yeah, obviously I wouldn't necessarily know that in advance. So it's always a challenge. How do you choose this? You know, so it's got to be big enough so that it works. So we can play around with that a little bit, but it's a lot of sort of interactive adjustment that you're probably going to want to do with the specification of the parameter values. Anyway, those are this variable here, Wolf underscore parameters. It shows them all. Okay, so now let's see what we do when we do some interactive fitting. I can show you sort of the workflow. Actually, let me pause for just a second and see if there's some questions before I go through and demonstrate the workflow. Is there anything that came through on chat that I should discuss?
I think we managed to answer the questions that were on chat.
Yeah. SP stuff does not have a GUI, right? That's true. Right now, it's done intended for being used in a notebook. Yep, it's a pip install. Okay, anything else? Okay, all right. Okay, anything else from those attending that you had a question that you didn't put into chat? All right, let me continue on then with the workflow. Okay, so now that we've got this function that's going to encapsulate our workflow, let's play with things a little bit. So as I mentioned before, just clear this so it looks a little, let's see here. Where am I? Oh, that's interesting. I don't know why it's behaving quite like that. At any rate, I'll leave it as is. Okay, if you're going to do a fit, a great way to start is to use, gradient descent, just to sort of see where you are. It's going to be fast, and who knows, you might be really lucky. So if we run gradient descent here, so that's do fit, the fitter methods. So what SBStart allows you to do is you can do multiple fitting methods. And as I pointed out before, this is sometimes really useful because some of the methods will get you in the neighborhood, maybe like a differential evolution, but it won't necessarily find the valley, and gradient descent will find the valley. So specifying sort of a fitting strategy of methods is actually useful. But in this case, we're just doing gradient descent. So if we do that, we run the simulation. So first of all, the first observation is, wow, this is pretty fast. We're fitting 16 parameters, and let's see what we came up with. Now, without an ability to compare directly the correct parameter values, which unfortunately I didn't do that out here. We could do that, but you don't see them. Some of these are clearly going to be off because we saw some that, I think this one over here was like 76,000, so we're off by quite a bit. You can look at the number of function evaluations. That's sort of interesting. It tells you, basically it's telling you it was fast, only 180. Chi-square is sort of, it may be big. We have to do some comparisons. The main thing that's going to be useful to you are going to be the plots. And you're looking to see how well the fitted value, which is the red line, matches the observed, which is the blue. And the main thing about the Wolf model, of course, are these glycolytic oscillations. And so you can see with the values of the parameters that were found with, this fitting algorithm and, this initial setting for the parameters, it didn't really capture the oscillations at all. I mean, there's some parts which are well captured, like some of these initial parts over here on each one of the species. but most of them, you know, it really, and this one over here, if you didn't know that there should be, or this one too, I guess you see it more carefully, but this one, it's even hard to see. If you didn't know that there should be oscillations, you definitely wouldn't see it from this. You'd say, yeah, well, it sort of goes through the points. It probably should be a little lower, but you know, what the heck? So, you know, obviously using a, you know, gradient descent, it was fast, but it didn't really get what we were after. Okay, so the next possibility is, well, let's try a different algorithm. We're going to try differential evolution. All right, so now warn you in advance. So let me tell you what's going on here. So in the process of doing the search, SB-Stoat will figure out, you know, other parameter values. So actually it's not so much SB-Stoat, it's really more differential evolution. We'll choose parameter values that may not be may not result in a solvable solvable integration for Roadrunner. And SVOD or CVOD rather is the integrator that's being used here. And so it may not converge. And that's what you're seeing here. There's no error in terms of the program. The issue is that you're not able to actually find some solutions. This all could have been masked, I suppose, but otherwise, you just see it like you're not sure what's going on. So for right now, at least, you get this reported. Now, let's see here. What I was trying to do is, unfortunately, can I get rid of this? I don't want to show the difference. I just want to get rid of this. Okay, well, I guess I can't get rid of that right now without something else happening. What you see over here, down here, this is the code executing. And what I can't see, maybe, let's see here. If I do this and I just say, oh, I may regret this. Let's see, now I have to get out of this, cancel. Okay, and then
you may just have it open in another tab that's doing a thing while it's...
Yeah, I don't know. Yeah, unfortunately, I don't. Well, that could be. No, I'm not so much worried about that. I just wanted to get rid of, oh, actually, in fact, I do right there. Thank you. Actually, now maybe if I save, it'll work. Okay, thank you. Lucian to the rescue again. Save failed. Yay. All right, well, I'll work it out. Anyway, well, this is a great way to pass time at least. So let me point out what's going on down here. So we're running differential evolution. Remember how fast it was with gradient descent? And differential evolution is a lot more complicated in terms of how the algorithm evaluates things in gradient descent. Go back up here. You can also see, again, a lot of these errors. It'd be nice to compress them, I guess. Okay, but if we go back up here to encapsulate workflow, it's probably easier to come down. So here we're running least squares, and we see 180 function evaluations. Okay, and if we go down here, fit the model, I guess I want to go down to below all this, probably limit parameter ranges. Okay. I guess we actually finished here. Okay, great. Okay, so let's get to the end of this. Okay, so let's take a look at what happened here. Okay, so here are the new values that we got for the parameters. Again, I'd have to compare them back to the originals to know exactly what's going on. In reality, you wouldn't know. The chi-square value is 9105. We can compare that up here to what did we get? Okay, here we got 38,000. So 9105 is much smaller than 38,000. So clearly, you know, we did something right with differential evolution just by changing the algorithm. Now let's take a look at what happens with the various fits on the parameters. So even though the chi-square is better, what seems to be going on here is that it's fitting still is not catching those oscillations. All right, so one of the questions is then, what happens? Okay, let me go down here just a little bit more. Yeah, okay. Sorry for that. slow. Okay. All right. So one of the things that we can do is we can change the settings on the parameter ranges. And that's what I've done over here is now this, in order to do this, of course, I had to know something about the true values of the parameters. So I'm cheating, you know, right away I can tell you I'm cheating. But what I'm trying to do is also show you how much of a difference it makes and how this is going to be likely an important part of your exploration. So we did differential evolution, but we set the parameter ranges for really large. And as a result, differential evolution may find something on the fitting surface that looks pretty good, but it's not our true values. It's not even close to the true value. So it doesn't capture a lot of those essential characteristics like the oscillations. Now, when I do this, which is a cheat, but it shows you a good direction to go, that this is something you should play with. What I did was I set the range to be between 0 and twice the true value of the parameter. So this one, the upper bound is 1100 and the true value is 550 and 2 and 4 and so on. That's what I did. But if I knew this, so I'd find this, it probably doesn't have to be just twice. It could be something a little bit better than that. Let's see what I do in terms of the results. So right away, remember before the chi-square was like 9100? I've got a much lower chi-square. And the most important thing is to look at what we have for fitting the oscillation characteristics. So a lot of the, I'm sorry, I'm in the wrong one. Here's the right one. Yeah, okay. So I'm sorry, the chi-square is 6389. Okay, so still lower than the 91 something. The main thing is by looking at how well we fit the data. You see, now we're capturing the oscillations in here, okay? And we could go back and check and see how close we are to the parameter values, but it shows you how this is another lever or another tuning point you want to use is to adjust those parameter settings. In some cases, you'll also want to specify the initial value. All right, so at this point, I think, you know, I encourage you to go through this exercise and take a look and, you know, play with it a bit. Let me see if there are any ending questions for this session, because for those of you in Europe who've hung on all this time, I commend you. And probably Asia too. I don't even know what time it is. I guess Asia, it's probably early morning. So maybe not so bad, or maybe bad in a different way, depending on whether or not you're a night owl. So any questions? All right, let me stop here. Let's see, I still see 32 people hanging on. That's impressive. All right, so let's see. Tomorrow afternoon, I'll talk about testing models. So that might be interesting to some of you, hopefully some of you as well. And then Thursday morning is going to be a discussion of some of these other sort of statistical refinements having to do with both this issue of dealing with variability and parameter estimates, and then also how do you actually design computational studies? Because it's not just about running a simulation. You want to try and evaluate some kind of scientific research question. Okay. Anything else? All right. I will. I'll see you tomorrow, and I guess you'll be in tomorrow. Okay, great. Take care.